we'll get to the physical applications. We'll be doing all those physics applications like force and work. Some of which should be familiar to you, I think. But before we get to the physical applications, we've got a few more examples of finding areas of surfaces. And we are looking specifically at surfaces that are created by rotating a curve around an axis. So we've got some curve, it's going to rotate around an axis, it's going to create a surface, not a solid, just a surface. And we are going to want to find the area of that surface. So when we are conceptualizing this idea, our generic formula is the integral of 2 pi r ds. So when we think about that formula, the 2 pi r is representing circumference. So you're imagining a point on this curve being rotated around the axis of rotation, creating a circumference. That circumference is 2 pi r. And then ds is a little tilted slant height, so that you're imagining this point with a little diagonal piece of curve that's going to create the base of a cone, the frustum of a cone. And the idea is that we're going to add up all the areas of these tiny frustums that are created as the points are rotated around the axis of rotation. So 2 pi r, that's circumference, and then ds, slant height. We don't know anything about s, so we convert the ds over to dx or dy, just like we did with arc length. So let's try one. So here's our function. There's a picture of it. We know we need the derivative. So the ds is where the derivative comes into play. So we'll have to take the derivative of the curve and then square it. So let's go ahead and do that first. So we're going to have y prime equals, we're going to do 1/2 multiplied by the base. So bring down the half, subtract 1 from the exponent, and then multiply by the derivative of the base. So there is y prime using the chain rule. And within the arc length formula, we know that we need to take the square of this. So let's go ahead and square it before we stick it into the square root function. So when we square all this, in the denominator, this 2 gets squared to be a 4. This square root is in the denominator, and when it gets squared, the square root will disappear, so we're going to have quantity 5x minus x squared. In the numerator, that quantity right there is being squared. 5 minus 2x is being squared. So that is y prime squared. So now we're ready to set up our integral. So the surface area, capital S, 2 pi r ds. So we're going to have surface area is 2 pi r. The 2 pi can factor to the front. R is the function. So that's going to be the square root of 5x minus x squared. So that is the function. And we're told that we're going from 1 to 4. So our limits of integration are as such. 2 pi r. Now ds, big square root, that's going to be 1 plus the derivative squared. We have the derivative squared right there. There's the derivative squared, and then we have to add 1. So I'll put the 1 in front, and then we've got the derivative squared right there. So that's going to be 5 minus 2x squared in the numerator. And in the denominator, we have all that. 4 times 5x minus x squared. So there is our integral. That's the setup for surface area. we know to combine two square roots, they become one square root, and you multiply the insides together. So the inside of this square root needs to be multiplied by the inside of this square root. So in other words, this quantity here is going to distribute to each of the terms within the second square root. And that's going to give us the following. So we will have 2 pi on the outside, integral 1 to 4. Well, first we'll take the 5x minus x squared and distribute it to 1. And this is all going to be within a huge square root. So we're going to have 5x minus x squared times 1. All right, that's itself. Now we multiply 5x minus x squared times the second term. It's in a numerator, so it's going to cancel with this denominator, leaving us with plus. We will FOIL out this numerator, getting 25 minus 20x plus 4x squared, all divided by 4, multiplied by dx. So all we did was distribute this quantity to the 1 and then to this whole fraction. And when it distributes to that fraction, it's common with this factor in the denominator, so those cancel in the second fraction. Now we simplify and cancel anything we can cancel. So the inside is going to become 2 pi integral 1 to 4 square root. So this 4 right here is going to distribute into every term in the numerator. When it distributes into this 4x squared, don't we end up with just plus x squared? That's going to cancel with that, negative x squared. So these two are going to cancel. That and that will cancel. When the 4 goes into the negative 20x, it creates negative 5x. Here's a positive 5x. So we're going to get a cancellation between this 5x and that. And the only thing that's left is not such a big quantity anymore. The only thing that's left is, I don't think I need the square root quite as big as I drew it. The only thing that's left is 25 divided by 4 inside the square root. All the x terms cancel. So that means that we end up with 2 pi. This is a constant. We'll bring it out to the front. That's 5 over 2. And what is the integral from 1 to 4 of dx? So how about in total, though? So this whole, if you integrate dx, you get x, but then you plug in a 4, you plug in a 1, you take the difference, so this whole quantity is equal to 3. Upper minus lower. If you integrate a differential, you get the length of the interval. You would get x evaluated at 4, which is 4, minus x evaluated at 1, which is 1, so you get 4 minus 1, which is 3. The integral of a differential is the difference in the endpoints. So we'll end up with 5 pi multiplied by 3, which is 15 pi. So that's the way we do the surface area ones. Question?
Does surface area usually cancel out at the end?
The ones we are going to see will cancel out pretty nicely. Maybe not all the way down to a constant, but they're going to cancel out quite a bit. If you get something really gnarly in here, there's probably an arithmetic error. Yeah?
The second to the last step here is with that.
This one here?
Yeah.
From here to here?
And before that.
From here to here?
Yeah.
From here to here, we're taking the square root of 25 and get 5, the square root of 4 and get 2. And then we're left with just the integral of dx. and the integral of dx is x. Plug in 4 for x, plug in 1 for x, and take the difference. So we get 4 minus 1, which is 3. So anytime we integrate a differential, it's upper minus lower, which we'll see a lot. Let's try another one. So here we have one that's going to rotate the other direction. It's going to rotate around the y-axis instead of around the x-axis. So that means that we have to write everything as x values instead of as y values. We need to be thinking of the function or the curve represented in a way that it's measuring horizontally instead of measuring vertically. When you isolate y, it's measuring vertically. When you isolate x, it's measuring horizontally. Formula in generic form, same, 2 pi r ds. Again, the radius is the function. The function, though, needs to be written as an x value. So we're going to come over here and say, oh, let's solve for x. So we're going to get x squared equals 4 times y. And x will equal plus or minus, dang it, I was too hasty when I turned on the computer, I think. So 2 times the square root of y. And now we have to decide, is this curve that we see in quadrant 1 the positive square root of 2y? Is it the positive 2 square root of y, or is it the negative 2 square root of y? It is positive, because we're in quadrant 1 where x's are positive. So that's our curve. That's going to be the radius then. So our formula will be s equals 2 pi, can be factored out to the front, integral, and the y values are going 1 to 4, the x values are going from 2 to 4. So now we have to look at the corresponding y values. The corresponding y values are going to go from 1 to 4 on the y-axis. So the x value of 2 corresponds to a y value of 1, and x value of 4 corresponds to a y value of 4. So we'll go from 1 to 4, 1 to 4, and then x, that is the radius, that's the distance over to the y-axis, that's the function that we have, so 2 square roots of y. And now we have our ds, so that's the square root of 1 plus the derivative squared. So 1 plus the derivative squared. We need to find the derivative, so we're going to come right here to the function that we're using, the function that's measuring the distance to the axis of rotation. We take its derivative, so this is going to be y to the negative 1/2. Or if you wrote it simplified, you would write it 1 over the square root of y. Yep?
Isn't the first limit of integration 2, not 1?
We're going in the y direction.
Okay.
So if we were integrating with respect to x, it would go 2 to 4. But the corresponding y values will be 1 less than or equal to y less than or equal to 4. So if we plug this x value of 2 in here, we get a y value of 1. If we plug the x value of 4 into there, we get a y value of 4. So 1 to 4. And then, like we've seen a bunch, we have to square this derivative. So x prime squared, well, that's just going to be 1 over y when we square it. So that is what ends up inside here, just 1 divided by y. So there's the whole setup. Once again, we're in a scenario where we have 2 square roots being multiplied together. So to combine 2 square roots, we multiply the insides together. So we take the inside of this square root, and we're going to have to distribute it to both parts of that square root. Yeah?
In this case, if we have 1 over y, can we just leave it as y to the -1? We don't want.
If you
fractions of-
want to, but it's going to be a lot easier to simplify most likely when you've gotten rid of negative exponents.
Okay.
Usually it's easier with negative exponents gone, but you can absolutely do it.
Okay.
For sure. Yeah, getting rid of negative exponents is usually the move. So that y is going to distribute, and it's going to create this. So the y gets multiplied by the 1, giving a y, and it gets multiplied by the 1 over y, giving just a 1. And so once again, we've seen that it's simplified pretty nicely to a point where we can integrate directly. And so we're going to use the power rule. We have our quantity y plus 1 raised to the half power. We integrate, we add 1 to the exponent, divide by the new exponent. So we're going to have y plus 1, I'll leave a little space. We're going to have y plus 1 to the 3 halves. Divided by 3 halves means multiplied by 2/3. And if the coefficient of y were not 1, we would also have to divide by that coefficient, which we would call the reverse chain rule. So if this was 3y plus 1, we would also divide by 3 as part of the reverse chain rule. Now we just have to plug in our limits of integration and take the difference. So we're going to have 8 pi divided by 3. Plugging in the 4 is going to give 5 to the 3 halves. And here's how we simplify 5 to the 3 halves. 5 to the 3 halves we write as 5 root 5. Minus, we plug in 1, and we get 2 to the 3 halves. 2 to the 3 halves we simplify this way, 2 root 2. And that is as far as we can go. Any questions on any of those steps? So the surface area ones often work out a little bit easier than just the plain arc length ones. The arc length ones, you often end up with really difficult integrals. But the surface area ones, usually there's enough cancellation that it's not too bad. Try another one. So once again, we've got a function that's going to be rotated around the y-axis. So we have a function of y. They've given it to us as a function of y. It's already presented as an x value. So it's already measuring horizontal, so that's perfect. And they've given us the y limits. So we don't have to do any finagling to figure out the limits or to change the look of the function. Again, anytime we're dealing with arc length or surface area, we need the derivative of the function that we're using that's measuring the radius. So x prime, chain rule, we'll bring down the 1/2. The base here is 12y minus y squared. That'll be raised to the negative 1/2 power. And then we multiply by the derivative of the base, which will be 12 minus 2y. So there's x prime. Any questions on the derivative? Chain rule, Ari?
What was the answer to the last one?
Say that again?
What was the answer to the last one?
Good question. 8 pi over 3 times 5 root 5 minus 2 root 2. Anytime we have this derivative, we need to square it. You know, when we look at that square root for the arc length piece, where does that square it?
On the last question, if you have different, like let's say we put the 3 inside the parentheses, or we
Here,
Yeah, change it, would it still be correct on the test?
totally fine. Yeah, this could be 8 pi multiplied by this whole thing divided by 3. Totally fine. You could distribute that if you wanted to. Usually we want our final answers factored, but it doesn't matter. Either way is going to be fine. Yeah. Doesn't, if they're equivalent, totally fine. Equivalent is good. So then we're going to square this quantity because we know that that arc length, the ds, that has a square in it. So we just look through here and square everything. The part that's in the numerator is the 12 minus 2y, so that's going to be squared. In the denominator, the 2 is squared to give a 4. This is a square root that lives in the denominator. When it's squared, we get just the inside here. We'll get 12y minus y squared. So there's the derivative squared. And now we're ready for arc length. So, excuse me, we're ready for surface area. So surface area is 2 pi times the radius. The radius is right here. The radius is the function when the function is written as an x value, when it's measuring horizontally. It's already written as an x value, so we're good to go. So we're going to just take the function, square root 12y minus y squared. All right, great. So there's 2 pi r. And they give us the limits of integration, 2 to 10. Now we have the ds. So the ds, the arc length piece, is the square root of 1 plus the derivative squared. Ooh, we already have the derivative right here, derivative squared. So we're going to have, and let's go ahead and FOIL out the numerator. So we're going to have 144 minus 48y plus 4y squared, and we'll hope for some good cancellation. And that's all divided by 4 times 12y minus y squared dy. So now we have same situation we've seen already a couple times. We have a pair of square roots that are being combined. To combine square roots, you distribute the inside. So we're going to have 2 pi integral 2 to 10. All right, let's see if we can distribute this and get some simplification. The 12y minus y squared first gets distributed to the 1. So that gives us 12y minus y squared. And now it gets distributed over to the second fraction, and it's going to cancel with that denominator over there, part of the denominator. Everything but the 4, it will cancel out that variable part of the denominator. So let's see, what are we left with? That cancels with this. All right. And then we're going to have to take this 4, which is left over, and it's going to distribute into the numerator. We have to take that 4 in the denominator and share it with each part of the numerator. So that 4 is going to go into 144. Let's see, what, 36 times? It's going to go into 48 12 times. And then that. Oh, and this looks a lot like one of the ones we did earlier. We end up with a lot of cancellation, the 12y and the minus 12y, the y squared and the y squared. So we're down to just a constant inside, which is 6. Square root of 36 is 6, and that's going to come out to the front and give us 12 pi integral from 2 to 10 of dy. And what's the integral of dy from 2 to 10? 8. Just the length of the interval. So 96 times pi will be our final answer. How'd that go? Reasonable? All right, so one more of these. Maybe I'm going to save this application one. It's not a real hardcore application. It's the same type of thing where we have to find the surface area, but then the application piece of it's asking for a volume of paint, where the thickness of the paint is 0.0015 meters. And so all we're going to do is find the surface area and then multiply by that thickness of paint, and that's going to give us a volume. But the part that we've been doing, same idea, we want the surface area of this surface that's generated by rotating that around the x-axis. Let's do that one on Thursday. I want to get to these physical applications because they take a little bit more, they're not quite as just straightforward. They're more conceptual than this stuff. So let's get to the physical applications. We can do that one on Thursday. If you've had no physics, I feel sorry for you. Has anyone not had any physics? Really? None? So that means you're probably going to have to spend a little more time than those that are more familiar with some of the physics. Because you've got a couple of concepts here that might be new then.
Does high school physics count?
Yeah.
Okay.
Yeah, any physics at all. Still no? None. Okay. All right. So the first equation that we deal with is the concept that mass is density times volume. And typically, this is when we have uniform density. So we've got the same density throughout an object. If that's the case, we'll take that density, multiply it by the volume, and we get the mass. Another way that's useful to rearrange this equation is to think of density as mass per unit volume. And for me, that's more intuitive. Right? When I think about density, I think of the mass of the object, and I divide it by the volume, so I can imagine the density of the object, possibly changing throughout the solid, depending on what the mass is at each point. So density can be constant. Like this formula is just assuming that we have uniform or constant density. And this would be if we have a constant mass, everything's constant, then we just have this nice little neat geometric formula. But density equals mass divided by volume is a little more conceptual, right? You can imagine taking the mass and dividing it by the volume and getting the density. So mass per unit volume. We are going to deal with another type of density in here. I would call this three-dimensional density when we have volume. You can also have a two-dimensional density. If you're thinking about a sheet of metal, you can think of that as a two-dimensional surface, and we would have 2D density where we would divide mass by area. You can also have 1D density. If you have a wire or a cable, you can imagine the density be given in mass per unit length instead of mass per area or mass per volume. So you have three different cases for density. In this class, we'll look at the three-dimensional case, mass per volume, and the one-dimensional case, mass per length. Imagine a hanging cable or something. So this is all well and good if the density is uniform. If the density is not uniform, well, then we find mass by integrating that variable density function. So if the density is not constant, you can't just use a geometric formula, you have to use an integral. Very similar to what we've been doing. If you want to find the area beneath this curve, that's supposed to be straight. That's very easy because the height is constant. We just are going to multiply, that distance by that distance. But if we have a variable height, what do we have to do to the function to find the area beneath it? We integrate it. So if you have a constant function, constant density, you can just use a little geometric formula, base times height or whatever. But if the function is variable, the function in this case is density if it's variable. If you have a solid object where the density is different at different points, then you integrate density to get to mass. So next slide is finding a couple of masses. The idea here is that we've got a thin bar, It's got variable density, so we're just imagining a thin little magnetic bar or something. And that's the density function. If we want the mass, all we do is integrate. So this slide is really a super simple concept. Sorry, I have some medical issues that I've got to help deal with. Okay, so we've got to just integrate the density to get to the mass. So the mass will be the integral of density, and this is as simple as it looks. We're just integrating the density function on the interval, and that will give us mass. So this slide is purely sort of that simplest case scenario where we've got a density function that's variable, and we have to integrate it, and there's nothing new here in terms of the math. So we're just going to integrate the density. This will give us the mass. We'll get 1 plus a fourth, which is 5/4. So in your mind, all you should be really at this stage thinking about is that mass is just the integral of density. So we're going to use all of our fancy integration techniques to evaluate these and to find our mass. So for an exponential, so this is just another example of using what we've called the reverse chain rule. Somebody tell me what this antiderivative is going to be. 100%, yep. Negative 5 halves e to the negative 2x. And we're going from 0 to 4. So remember, the antiderivative for an exponential is itself. So we rewrite the function, 5e to the negative 2x. But then we look up into the exponent position, and we are taking the derivative of the exponent, which is negative 2. And the reverse chain rule says when you're integrating, you divide by the derivative. Similar to the chain rule where you multiply by it, but when you integrate, you divide by it. And that will give us our antiderivative. And then we're going to go ahead and plug in our limits of integration. So I'm going to think of the negative 5 halves out in front. So negative 5 halves. And then I'm going to plug in 4 and get e to the negative 8 minus e to the 0, which is 1. So there we go. So that is our antiderivative, which represents, in this case, the mass of that thin magnetic bar, thin metal bar, whatever, however you want to think about it. That is its mass. Is that number positive or negative? No.
Positive.
Yes. Everyone see that? It's positive. Isn't e to the negative 8 minuscule? So minuscule minus 1 is negative. Negative times negative is positive. So for finding mass, mass has to be a positive number. So just want to make sure that we see that that is a positive number, because that term there is super small, minuscule. All right, so let's go ahead and do some work. The first physics example you ever do in any physics class is the spring. The first real example is the spring. The spring is, it's got, every spring that you deal with has a spring constant associated with it. It's very similar to what you did in algebra when you were doing those radioactive compounds that had a decay rate associated with them, decay constant. Same idea. Every spring has a unique spring constant, which is an indication of how much force is needed to compress it or to stretch it. And what's amazing about the spring is that where's my formula? Oh, I guess it's going to be on the next slide. The amazing thing with the spring is that once you have the spring constant, the force that it takes to compress or stretch a spring is a linear function. It's just F equals kx. The force function is a linear function. which is cool. You might think that with a spring, it might be an exponential function that represents the force. It might feel that the force required to compress it the second inch is way harder than the first inch. But it's not. It's just a linear function. So that makes it very easy to integrate. So the concept here is as follows. So when we deal with work, we again have like a simple geometric formula if the force is constant. So if you apply a constant force to an object and shove it across the ground for a specific number of meters, the work that's done is simple. It's just force times distance. Very similar to the area of a rectangle. Base times height, force times distance. But as soon as that force becomes variable, as soon as the height becomes variable, as soon as the density becomes variable, we use an integral. So if that force function is variable, then we have to use an integral to get to the work done. When the force is constant, it's just force times distance. So simple enough. But when the force is variable, so here they're saying, okay, let's apply a variable force. And when that force is variable, instead of just force times distance, we imagine, if we want to go to the Riemann sum scenario, we imagine tiny little movements. We break it into little pieces. And on a little piece of distance, the force is essentially constant. And so we have this little piece of force times this little piece of distance, which will be the little work done to move it a minuscule amount. And then we add them all up, and we get the total work done. We take the limit of the Riemann sum. The limit of the Riemann sum becomes the definite integral. So the definite integral, that's what you learned in Calc 1, that the limit of a Riemann sum, as your little subdivisions become closer and closer to 0, the limit of that Riemann sum becomes the definite integral. So that was your Calc 1. So let's use that. So here we've got a spring. Equilibrium, the spring is just sitting there on a table. We're going to call that x equals 0 when it's at equilibrium. If you stretch the spring from equilibrium, we will say that the force is positive. Force is a vector. It's got direction and magnitude. So that force is positive, means you're going to pull it in the positive direction. If you're going to compress the spring, the force is negative. So there's going to be a magnitude to the force, but there's also a direction. So that force is compressing the spring. And as you probably can intuitively realize, if you compress the spring an inch, or you expand it an inch, stretch it an inch, the work done is going to be the same. The force is going to be negative in this direction, positive in this direction, but it's going to take the same amount of work to compress it an inch as it is to stretch it an inch. Work will be positive in both cases. So work will be positive. So the formula that we use to analyze a spring is F equals kx, where F is the force, K is the spring constant, and X is the location on this axis. So if it's at equilibrium, X is 0. If you're stretching it, X is positive. If you're compressing it, your X value would be in the negative side of the equilibrium position. So let's try a force with a spring. So somehow we need to figure out what K is for any given spring. Just like those radioactive isotope things, the way that's done is to take a moment in time, and what they tell us here is that it takes 15 newtons to stretch and hold a spring 0.25 meters from its equilibrium. So let's write down the math for what that says. It says it's going to take a force of 15 newtons. We don't know K, and that's going to stretch it 1/4 meter. So that moment in time right there, we get a data point. We know that it's going to take 15 newtons to stretch it 1/4 meter. That's how we find K. So we have to have this one data point in order to get the spring constant. All right, so this tells us then that our forcing function is 60x. So for this spring, that's the force function. That force function is going to be used for this spring in any problem we have. So this is part A. So part A says assume the spring constant obeys Hooke's law, find the constant. So there's part A right there. And then part B says how much work is required to compress the spring 0.2 meters from equilibrium. So we're going to integrate our forcing function. And then our limits of integration represent where the spring starts and where it ends. So it says it's going to start at equilibrium, and we are going to end up compressing it 0.2, so negative 0.2. So negative 0.2, I'm going to write it as a fraction, so negative 1/5. So there is the setup. So this will be the work done in compressing it 0.2 meters. It's also going to be the work done in stretching it 0.2 meters. So if I wanted to write the stretch, it would look like this. And I claim that it's going to be the same. Let's see why it might be the same. So it's going to be the same. So this one on the left, this is a compression. That's a stretch. Let's focus here on the left here. If we integrate, we get 30x squared from 0 to negative 1/5. Oh, now it's obvious why it's the same work. If you were to plug in a negative 1/5 into this x, or a positive 1/5, because that x has a square on it, you're going to get the same work. Everybody follow that? Because that antiderivative has a square in it, you're going to get the same work. So we're going to get 30 multiplied by 1/25, which if we divide out of 5, we get 6/5. Units of work, when we're dealing with meters and newtons, units of work are, what do you think? Force times distance. For force, we use units of newtons. Distance, units of meters. So work is a newton meter, which also has another word that we use sometimes, which is a joule. So you can use either newton meters or joules. It doesn't matter. So a newton meter, usually you hyphenate it, or you could say 6/5 J for joule. So either of those is totally fine. All right, let's take a look at C. So C says how much additional work, is required to stretch the spring 0.3 meters if it has already been stretched 0.25 meters. So we don't know anything about how much work it took to stretch it to 0.25 meters. We want to know this. We want to know the work done in taking it from 0.25, that's where it's starting, and we want to stretch it another 0.3, so our terminal x value will be 0.55. If our x position is 0.25 and we stretch it another 0.3, that's going to put it at 0.55. We have the same forcing function, same spring. So that's what that integral will look like. That's going to represent the additional work, starting at 0.25 and moving at 0.3 more. So that's going to be the integral we want to solve. And once again, antiderivative is going to be 30x squared. It's usually best to go to fractions and not be dealing with decimals, usually best. So I'm going to go to 1/4. And up here, 55 hundredths. So 55 hundredths, if we divide out of 5, we get 11/20. So plug and chug here, we're going to have 30 multiplied by, we square this, we're going to get 121 over 400 minus 1/16. And then whatever that simplifies to. Plug it in your calculator, turn it into a fraction, and whatever that simplifies to. And units will be joules. So, units of joules. So the spring is kind of our basic application. We're only integrating a linear function, so it's not that complicated. The hardest part usually is making sure that you have the right limits of integration. But again, the concept should be pretty straightforward because we have a linear function and work is force times distance. Stretching, compressing, same amount of work to go the same distance. Question?
Where
Aiden?
did the 0.55 come from?
That was given. So, or indirectly it was given. So it said it's already been stretched to 0.25. So the spring is at 0.25 centimeters beyond, or meters beyond equilibrium. And then it says we want to go 0.3 more. So we want to go 0.3 meters if it has already been stretched 0.25.
Oh, okay.
You see it? So we're at 0.25 and we want to go 0.3 more. So we're going to go from 0.25, 0.3 more is going to put us at 0.55. Does that make sense?
Yeah.
All right, so there's the spring. Let's do one more spring. So calculate the work required to stretch the following springs. So we're going to stretch 0.4 meters from their equilibrium, assuming Hooke's law is obeyed. So part A. Let's do A first. And part A is very similar to what we just did. So they give us newtons and they give us meters, and we can plug those directly into Hooke's law and we can get the K value for this particular spring. So we're saying to ourselves, oh, okay, it takes 50 newtons to be stretched 0.1 from equilibrium, so that's a tenth. So 1/10 multiplied by K. So that tells us that our K value is going to be 500. So that tells us that our force function for this particular spring is 500x. So we take that one initial value and use it to find the spring constant, and now we can do what the problem asks us. How much work is done to stretch it from equilibrium to 0.4? So we're going to take the function 500x and integrate it on the interval 0 to 0.4. This will be 250x squared from 0 to 0.4, which is again 2/5. Change it to a fraction. So the work done will be 250 multiplied by 4/25, which will be 40 joules. All right. So that one follows the pattern that we saw in the last couple, where you get your K value by looking at some initial value where they give you force and they give you distance. Let's take a look at this next one. This next one's a little different. So we know that we're dealing with F equals Kx, Hooke's law. But here, the initial value that they give us is not force and distance, it's work and distance. So a little bit different. So here's how we're going to set up the equation in order to find this spring constant here. So we know that work is equal to the integral of force. So it's integral of Kx. And what they're telling us here is that, oh, we are going to get 2 joules of work is going to be done if we integrate this Kx, where we don't know K, but we know K is a constant, and we're going to integrate it from 0.1 from equilibrium. So we're going to go from 0 to 0.1. So that's the equation that they're giving us, initial value with the work done. So we know W, and we know our limits of integration. All right, so we can integrate that. So we're going to have 2 equals kx squared over 2. Add 1, divide. We're going to go from 0 to a 10th. We can multiply that 2 out of the way if we want. We can make that 4 equals kx squared from 0 to 1/10. That might be easier just to clear that out. All right, so now we plug in 0, get nothing. So all we care about is the upper limit of integration. So that's going to be k times the 10th squared, which is 100th. So this k value is going to be 400. So that's the k for this one. And once you have the k value, that tells us, therefore, the force function for this is going to be 400x. So for the spring in part B, it's got a different force function. We still are asking the same overall question, though. They said, well, how much work does it take? How much work does it take to stretch it to point 4? So the only difference now is that our work to go from 0 to point 4, we're just integrating a different function. So that forcing function is just different. So a lot of it looks the same. So we're going to get that amount of work, 32 joules. All right, any issues with the spring? So the spring is kind of the most basic application that we'll look at in this section. And now we're going to get to the more interesting applications. So the same basic principle is going to apply. Work is force times distance. But now we're going to talk about introducing gravity. So with the spring, you're thinking about the spring lying on its side. We're not having any gravity business going on with stuff happening vertically. So now we're going to talk about something that does involve gravity. So we still have work equals force times distance. But as soon as we tip our situation vertically, we are going to deal with gravity. And so we're going to call these lifting and pumping problems. And when we go vertical, force is going to be given by mass times gravity using Newton's law. So mass times gravity is going to be how we find force. Unlike the spring, where we found force to be kx, if we're going vertical, with gravity, we have force is going to equal mg. So mass times gravity. And there is the integral for work. Yeah, looks like a mess. I'll give you a way to memorize this very easily in a second. So let's just suppose we're going to use the Riemann sum idea, blah, blah, blah. The Riemann sum idea is going to give us this integral when we take the limit. At this stage of the game, we need to know how to replicate that integrand without creating an aneurysm. The ideas are simple, though. We take slices. We imagine our vessel filled with water or whatever. We take a slice. We're going to figure out how much work it takes to pump out each slice or to drain each slice. We're going to add up all those works and get a total work. You know, the same idea. Here's the integrand. I've labeled some things here. This capital A is the area. If we have our vessel filled with water and we take a cross section, that's two-dimensional. That's the area of the cross section. The D here is the distance that cross section has to either drain down or the distance it gets pumped out. So we either have a situation where water is being pumped out the top or drained out the bottom. So area cross section, d is the distance traveled. Rho, that's that funny looking P. That rho is density. Density of water is always going to be given to us. It's 1,000 kilograms per cubic meter. G is gravity, 9.8, magnitude of gravity. And then there's dy. So all these things are labeled here, and you can look at it carefully. But what I want to focus on is the next slide, where I sort of give you a better idea of how to create this. So here is an acronym that I find super easy to replicate that integral every single time. So here we go. So if we want to find work, we're going to use this acronym, ADD volume. ADD is a very easy word to remember. It's a math word. ADD, we're going to add volume. So ADD volume, anytime we're finding work when we're lifting or pumping, ADD volume will give it to us. In the next section, when we get to force, so this is for work, when we get to force, instead of ADD volume, we use ADD area. We'll talk about why when we get there. If I were you, I'd look at all these units carefully. A lot of times to know in physics whether you've set up your integral right, the units for each of the factors has to match and give you what you need in the end. So that's always a good thing to do. Now, a rope or a cable hanging, if you want to find the work to lift it or drop it, it seems like it should be easier because it's only one-dimensional density. Let's do the one-dimensional densities after the three-dimensional ones. The three-dimensional ones are actually more intuitive. So let's come back and do the rope and the chain in a minute. Let's do a 3D one first. So we'll do one example. This is the simplest 3D one, and then we'll take our break. So here's the scenario. We've got a cylindrical tank. It's filled with water. It's 8 meters in height, 2 meters in radius. Tank's full of water. We're going to pump it right out the top of the tank. How much work does the pump do? Another scenario that would give us the same exact answer is how much work does gravity do if we just puncture it in the bottom and let it all drain out the bottom? It's not always the case that the pumping work will equal the draining work. But in this case, where the object is symmetric, the pump will do the same amount of work that gravity would do if you let it drain out the bottom. Not always the same, but in this case it would be. So here's what I'm going to say to myself. Work, three-dimensional, dealing with gravity. This is the integral of ADD volume. So I'll always write it like this. And now we just have to make sure we understand what each of the letters in the acronym mean and what we mean by volume. And let me just say before we get going far, that volume is not the volume of the tank. It is the volume of a slice. So if we take a cross-section is area. And if we add thickness to it, we get what we call a slice. So cross-section is two-dimensional. And then if we puff it up just a tiny amount, we get a slice, which is three-dimensional. And that volume is the volume of a slice. So when we're thinking of that volume, we are thinking of this. We are thinking, OK, here is a representative cross-section at y. And if you puff it up a little bit, you take a little bit of height right there. Now you have a slice. And the volume right here is the volume of a slice. Not the volume of the whole tank. It's just the volume of a slice. It's going to include the dy. dy is that minuscule height. But it's nonetheless three-dimensional. It's a solid now. That slice is solid, and its thickness is dy. That's going to be part of volume. So the differential is part of the volume here. So here we go. So the work done, A, acceleration. Acceleration due to gravity, 9.8, unless we're in the other system. So 9.8 metric system. Acceleration, density, distance. Density, the density of water, which will, right there, which will always be given to you. So the first two letters, the first AD, almost always is 9.8 times 1,000. Acceleration, density, distance. You can also think of that D as representing depth. Distance means how far does that slice have to travel. If you're pumping out the top, we want that distance. If we were draining out the bottom, we would want that distance. So how far does that slice have to travel? Well, what do you think?
8.
From there to there is 8? There to there is y. 8 minus y. Yeah, so 8 is the full height. That, if you're right here at a height of y, that distance right there is going to be 8 minus y, because this distance right there is y, because that's what that y represents. That y is representing the distance above the bottom of the tank. That's the height. So the distance this slice is going to travel will be that distance, 8 minus y. So that slice right there is going to travel less far than that slice. Right? So we're going to always have that's a function. The slices are traveling different distances, which means each slice takes a different amount of work to get it out the top. Right? So the work is going to be variable because the distance for each slice to move is different. Okay, so the distance is 8 minus y. All right. So that's the ADD. Now we want to deal with the volume. So there's ADD, acceleration, density, depth, or distance. Volume, volume of slice. Not volume of tank, volume of slice. Okay, so that purple slice, we want the volume of it. Oh, it's a disk with thickness. So its volume is the area of the cross-section, pi r squared, multiplied by dy, the thickness of it. So this is 2 meters across. So what is the area of the cross-section? Pi times the radius squared, so 4 pi. So every cross-section will have an area of 4 pi. So that's the area of the cross-section. But then we need to multiply it by the thickness, or the height, but it's a minuscule height, so it's a dy. So that right there. That is the volume that we are looking for. That is the volume of a representative slice. What do you think the limits of integration will be? 0 to 8. Because we have cross sections of water all the way from y equals 0 up to y equals 8. So we'll go 0 up to 8. There we have it. So there's the setup. There's a boatload of constants in here. So we're going to factor them all out. 9800, a 4 pi, 0 to 8. The only thing that's not variable is 8 minus y. Everything else got factored to the front. And so we can multiply the 4 and the 9800. I'm just going to not do it for a moment because maybe there's going to be some cancellation that might come out of this. So we integrate. We're going to get 8y minus y squared over 2 from 0 to 8. So we're going to get 9800. Not going to multiply quite yet. Plugging in 0 gives nothing. Plugging in 8 gives 64 minus 32, which is 32. And that is our answer. We just have to multiply those things together to get our total number of joules. So we're going to do 9800 multiplied by 4, multiplied by 32, and we're going to have a whole bunch of joules. 125,4400 times pi joules. So that's 1,254,400 times pi joules. So that is how we will do the pumping problems. So overall, as long as you can keep the right acronym, and remember, they actually aren't as complicated as the original slide made them feel. Acceleration density depth, or acceleration density distance, however you want to think of it, times volume. Just remember that we're finding volume of a slice, not the volume of the tank. Volume of a slice that's cylindrical, cross-sectional area times dy. All right, let's go ahead and take a 10-minute break and stretch. Stretch your brain. Ask me a question during the break if you are so inclined. Thank you. So, the other thing, when we were talking about the Calc 2, the other thing to keep in mind is in Calc 2 we go a little faster in the first few weeks because the stuff in the middle, the infinite series, is the hardest stuff, and we have to go a little bit slower with that stuff because it's so hard. So we're covering more sections per day, if you think of it that way, the first unit. Because in the first unit overall, the content is actually the easiest that we're going to see. So in the middle unit, we're going to go a little slower because it's harder. So the first unit is fast for sure. What's that? It's actually, I said unit 2, but unit 3 is the hardest. The infinite series, chapter 10 and 11. That's the hardest. Many people say that's the hardest in the whole Calc sequence. Calc 1, 2, and 3, chapters 10 and 11. The hardest.
Because it's just a bunch of.
So we definitely do go a little bit faster in the beginning because as you start to do the homework, this stuff, in terms of time it takes, will be less than what's coming down the road. So we do go faster in the beginning just to try to hedge ourselves when we get to more complicated stuff. Oh, man. I gotta take this. Hold on one second. Oh, nope. They'll leave a message, I guess. Okay, so trough, same idea that we just saw. We're going to be pumping the water just out of the top. What is the geometric shape of each cross section? Yes. Rectangle. Does everybody see that each slice is a rectangle? Because the slices are horizontal, we're dealing with gravity, so the slices are horizontal, not vertical, so each slice is going to be a rectangle. So when we find the area, the cross-sectional area is just a rectangle, and then we multiply by the thickness. Now the thing that's going to be hard about finding the cross-sectional area is that we need to know the distance straight across. All right, I got to take it this time. Hello, this is Jim. Yes, how's it going, Carla? Let's go ahead and try to fill in the blanks here. So once again, we're dealing with work, and we're dealing with a three-dimensional case that involves gravity. And so that means that we're going to use our acronym for work, which is ADD volume. And once again, volume is not the volume of the trough. It's the volume of a cross-sectional slice, which is a rectangle multiplied by dy. So when you're envisioning this, you're imagining a rectangle of water. And so that rectangle of water, if I draw a representative one, it's going to be something like that. So there's a representative slice of water. we know this dimension, right? That's just 3. That's easy. That's given. The hard part is knowing this dimension. And this dimension is hard. I'll call it W because it's going across the semicircle. So we have to find a distance across the semicircle, horizontal distance. So we're going to have to write the equation for this semicircle. We're going to have to write the left half as a x equals negative, blah, blah, blah. The right half is x equals positive, square root of blah, blah, blah. And measure that distance across a semicircle. So that's going to be the hard part. So let's start filling in blanks. So acceleration is just 9.8 and density. So acceleration, density, distance or depth, those two almost always are the same.
For the trough, will it always be like we'll do rectangles in a trough?
Yeah, always. Yeah, if we have a trough, it'll always be rectangles. So you're always dealing with base times height. The question is, if this is a trapezoidal face, then finding the distance across is a little bit easier than if it's a semicircular face. So regardless of the type of trough, this dimension is always given. But finding W depends on what the shape of the front of the trough looks like, whether it's trapezoidal or whether it's semicircular. Sometimes it's a V. So finding that distance across is going to be the tricky part. What do you think the distance or depth is? So if we're going to pump this cross section out the top, and it's filled, what do you think the distance that slice has to travel? Not quite, because let's just imagine this slice right there. It's not going to travel the full radius. It's going to travel the radius minus y. So if we draw a picture of the face of this, so if we think about the front of the trough, let's draw it semicircle like that. And then I'm taking a representative cross section right there. The radius of this trough is a quarter. So this point up here is 0, 1 quarter. So, and that cross section right there is at a random y. So how far is that cross section of water going to travel?
3 minus y.
Close.
Y minus 4.
Where's the 3 coming from? Oh, no. Yeah, it's going vertically, right? So the semicircle is a quarter in height. So it's going to be a quarter minus y. Right? Quarter minus y. So the distance it will travel is 1 quarter minus y. So 1 quarter minus y. So very similar to the last one. This distance right here is 1 quarter. This distance right here is y. So the distance it travels is a quarter minus y if it's going out the top. Yeah?
How would it then be if we're going out the bottom?
So if we're going out the bottom, how far does it travel? Y. Right? So if you're draining it right out of the bottom, the distance it's going to travel is y. Yep. Okay, so we have our ADD, acceleration, density, distance traveled. Now we need volume. So volume is going to be the area of that rectangle. The area of that rectangle is going to be whatever W is times 3. So it's 3W dy. That is the volume. 3W dy. 3, length of the trough. W, width of the trough. dy is the thickness of the slice. It's what adds volume to that two-dimensional cross-section. That's what makes it three-dimensional. And what do you think the limits of integration will be? 0 to 0 to a quarter. We're going to have all these rectangles stacked on top of each other from y equals 0 up to y equals 1/4. So that is our setup. Yeah?
Shouldn't you also represent W in terms of y?
Yeah, we have to. because we can't integrate w with respect to y. So that's the next step is, okay, well, what's w in terms of y as a function of y? Yeah.
Could you also do this the other way if you were sliding the semicircle across?
No, because each cross section has to be set up in a way that all the points in that cross section travel the same distance. Because work is force times distance, so we want a collection of points that are going to have constant work. So if you take a slice of water this way, each one of those points is going to travel the same distance, so to move each point is going to take the same amount of work. As soon as you go this way,
That's when you do it.
that's going to be different, because this point's going to take more work to move from here to here than this point will take.
That's when you slide the semicircle.
Yeah, exactly. So if we're going the other way, yep. So now we have to figure out this W thing. So we come over here. W is that distance across that semicircle. Let's first find the equation of the semicircle and solve for x. Lawson?
And W is the width of the semicircle at any point in the slice.
Yes, exactly. So W is going to go across, and it's going to tell us the width across the semicircle for any y value. So if we say, oh, let's let y equal 0.1, then we're going to get the width across as a function of y. So then we can get W when y is 0.1, when it's 0.2, whatever the y value is. So, equation of a circle. So equation of a circle. What is the equation of a circle? So this circle is centered at 0, 1/4. So its equation is x minus 0 quantity squared plus y minus 1/4 quantity squared equals the radius squared. The radius is 1/4, so that's going to be 1/16. So that's the equation of a circle centered at 0, 1/4. We're trying to find horizontal distances here. So what letter do we need to isolate? X or y? X. So we're going to have x squared on the left equals 1/16 minus, I'm going to FOIL this out. This is going to be y squared minus quarter times y doubled. Quarter times y doubled is 1/2 plus 1/16. So the 16ths cancel. We're going to get x equals plus or minus the square root. These 16ths cancel. So we're going to get x equals plus or minus, see what's left. Minus y squared plus 1/2 y. So that is the right and the left semicircle. So this one on the right, does it use the positive or the negative? Positive plus 1/2 y. And the one on the left is the one with the negative. So this is going to be x equals negative square root of negative y squared plus 1/2 y. Okay? So what does that make W? Therefore, W equals right minus left. So root minus minus root. That gives us 2 times the root. So there is the mysterious W. So that tells us the width across the semicircle for any y value. If you plug in 0, you get 0. If you come all the way to the top and you plug in 1/4, what do you think the distance should be across there? If you go across the diameter, the distance should be, if the radius is 1/4, the distance across the diameter should be 1/4 plus 1/4, which is 1/2. So if you plug in 1/4, so you come up here to a y value of 1/4, if you plug that in right there, this whole thing better simplify down to 1/2. You could do it and make sure that it's right. So now we can go back to our integral and we can do the integration. So the 9800 is coming to the front like it almost always does. And let's just pull that out for now. We'll see that there's other stuff that can be pulled out for sure. But let's just do that. So then 3 times w is going to make 6 times the square root of negative y squared plus 1/2 y dy. All right. So let's factor the 6 out. So the 6 is going to come out. I should try to move some of this stuff over a little bit. So the 6 comes out and gets multiplied by the 9800. I tend to just wait instead of combining things right away because a lot of times there's division that will make things a little bit easier. So let's take a look at this and see if we can integrate that. So that's where we're at. The only hope we have to integrate this is using substitution. It's the only hope. We've got a function inside the root right there. And we've got a function outside the root right there. The only hope that we have is that we could let u equal the inside and somehow it might match what's on the outside. It's our only hope. Let's see if that's going to work. So we would let u be the pink, minus y squared plus half y. Let's come down here. U equals, I already forgot what it was. Oh yeah, it's just this right here. Minus y squared plus 1/2 y. All right, so let's suppose that's used in the square root. We'll take the derivative and see if we can match the function that's out in front. So that's minus 2y plus 1/2 multiplied by dy. So I'm going to go back up here and look at what my target is. So the target is that. We need just y. So what I'm going to come down here and do is divide everything by 2. So if I divide by 2, we're going to have negative y, divide a half by 2, we get a quarter. So we have that. So negative y plus a quarter times dy will be du over 2. So let's see if that helps us. So negative y, oh, right there, negative y plus a quarter. That matches. Negative y plus a quarter is du divided by 2. So we are golden. So we're going to have 9800 multiplied by 6. We're going to have a division by 2. And this is going to be the square root of u multiplied by du. So the pink is what we let u be. So we have the square root of u. And then the other part, the green part times dy, is du over 2. So the du over 2, we can put the over 2 out in front. And that's an integral that we can manage. And we have two choices. We can convert our limits to u, or we could just put placeholder limits here and go back to the y limits in the end if we want. Doesn't matter. When I look at these here and I think about plugging in a quarter, I'm going to get an eighth and a 16th. Maybe you don't want to deal with that and you want to go back to the y's in the end. It doesn't matter. Or you can switch to u's. Because we haven't done it this way, let's just put placeholders. Let's not find the u's. I'm just going to put some little stars here and say, oh, we'll get the limits later. We'll deal with the limits later. So now we have 9800. Let's cancel out a 2. So we have that. And then we integrate here. We're going to get u to the 1/2, add 1, u to the 3/2. So u to the 3/2, dividing by 3/2 means multiplying by 2/3. And we have just placeholder limits for now. Star and double star. The 3's cancel. So now we're left with 9,800 multiplied by 2. And now we have to go back. Since we're not going to use u limits, we're going to go over here and say, oh, well, y is equal to, or u is equal to that, minus y squared plus 1/2 y. All that's raised to the 3/2 power. And we go to our y limits, which were 0 to 1/4. And still, we're going to still have to do a little bit of work, but that's where we're at. Okay, so we have 9,800 times 2, which of course we can multiply it whenever we're ready. Plugging in 0 gives nothing. We're going to have minus 1/16 when we square the quarter, plus 1/8, all raised to the 3/2 power. So that is our answer. So this will be 9,800 times 2, negative 1/16, plus 2/16 is 1/16. So we're going to have 1/16 to the 3/2. Anytime we have a 3/2 power, we do the denominator first. The square root of 16 is 4. And then we have to cube the 4. So 4 times 4, 16 times 4, 64. So we'll put that there. And then we'll just simplify that. So whatever that simplifies to will be our final answer. So 9,800 times 2 divide 64. Turn it into a fraction. So we get, how do I turn it away from a mixed number on here? I know there's a way, but I forget. So 1225 divided by 4. And units are joules, because we're finding work.
For the limit bounds, how did you get 1/4 from 0 again?
So when we're looking at our trough, the trough is filled with water. So there's water that's going from 0 up to the radius of that semicircle. And the radius of the semicircle is 1/4. So that's given to us that the radius is 1/4. So that's going to be that distance from down there up to this diameter.
So I get where that's coming from, X, but then when we change it to U, in the next line we have the Y.
So
the U.
we never found the U limits.
Okay.
So we never found the U limits. And so at this stage right here where we have U, we look back over here to what U is in terms of Y. So U is negative y squared plus 1/2 y. So we replace U with negative y squared plus 1/2 y. So that gets replaced with U, what it's equal to. And then we still have the 3/2 power. Now we're back in y, so we use y limits.
Okay, so.
Yeah. So we're going back to the y limits instead of using U limits.
Okay.
So we could do either.
So you pass it to the negative y squared plus hash y?
Mm-hmm.
Oh, okay.
Yep, so we're going to take that U and replace it with that. That came from letting U be what was inside the square root originally. Yeah?
Can you explain the wording in part A?
Yeah.
What it means?
The wording in part A. How much work is required when the water, so when it's full. So that's why our limits go 0 to 1/4, because we're assuming it's full. Like if the water only went from 0 to, say, 1/8, so it wasn't full, then we would have our limits of integration go from 0 to 1/8. So when the trough is full, full would be 0 to 1/4, right? The limits of integration are going to match whatever the physical scenario is. So if the trough is filled all the way up to that diameter there, then the limits of integration go 0 to 1/4. If it's filled up less, then the work done is going to be reflected by changing the limits of integration.
So the to the level at the top of the trough means all the way.
Yeah.
Okay.
Yep, exactly. And then if the length is doubled, is the required work doubled? So if we think about this 3 right there, that's the length of the trough. If the trough is just doubled in length, what does this become? 6, and that just still factors to the front, so that's a yes. If we double the length of the trough, we're going to double the work, because that 2 will just end up being a multiplier out in front. How about this? If the radius is doubled, is the work doubled? So if the radius is doubled, so that means this trough is going to look a lot different. If the radius is doubled from 1/4 to 1/2, no way is the work just doubled. If we change the volume, it's going to be a totally different problem. If we just add length to it, though, that's different. But if we increase the shape of the trough, that's not just going to double it.
Would it be by a factor of 4?
I don't think so. You could try. That's a good question. What would the difference be? That's a great question. If I have a minute after class, I'll take a look at it. I don't think it's that simple, though. Okay, so the simplest vessel that we had was the cylinder, because every cross-section was the same. Trough, much harder because we've got that semicircle. Anytime we have a semicircle, we just take a deep breath, because semicircles are a pain in the neck. The cone is the second easiest shape that we can deal with. So let's take a look at the cone. So now we've got this water tank shaped like an inverted cone, 6 meters high, 1.5 meters in radius. And we're going to pump it out of the tank. How much work does it take? Okay, so once again, we're in the scenario where we're finding work. So work is going to be the integral of ADD ADD volume. ADD volume. And the first bits of this are pretty similar, right? We always are going to get acceleration, 9.8. The density of water is 1,000. And now we need the distance traveled by a cross-section. So we're coming over here. We're going to draw a cross-section. There's our cross-section. That's a cross-section at a random y. So this is the distance that it's going to travel. How far is it going to travel? 6. 6 minus y. So 6 minus y. Okay, so those are the 3 pieces that should be pretty immediate. Acceleration, density, distance traveled. And again, the whole distance is 6. This distance here is y. So this distance up here is 6 minus y. Now, volume. This is the harder part. So volume, it's not the volume of the vessel. It's the volume of that slice. The volume of that slice is the area of the cross-section multiplied by dy. So we know that the area of the cross-section is going to be based on the radius of this circle right there. I'm going to put an r there. So for the time being, I'm going to just call this pi r squared multiplied by dy. So pi r squared dy. So that is the volume. But of course, we have to change the r into y's. We have to find r as a function of the height, as a function of y. So let's come over here. And what about limits of integration?
0 to 6.
Yeah, if the thing is filled, 0 to 6. If it's only halfway filled, if it's only filled to 3, we would integrate from 0 to 3. So the limits of integration always match where the location of the water starts. Okay, so then we get 9,800 pi. So all that's coming out. We have 0 to 6. We have the 6 minus y. Okay, now we have to deal with this r squared business. So we come over here. We need r as a function of y. And it's actually way easier than it might sound. Let's press this into 2 dimensions. So if we press this into 2 dimensions, we have this scenario right here. So the the line right there is, it is a line, right? What is the equation of this line? So the rise is 6. The run is 1.5, which we could write as 3/2, multiplied by x. Right? That's the equation of a line. Especially if it goes to the origin, it's really easy because then it's just slope times x. So it's rise over run multiplied by x. If it goes right through the origin. So if we, simplify that coefficient, dividing by 3/2 is multiplying by 2/3. So isn't that going to be y equals 4x? Everyone with me? 4x there. 12 divided by 3. Now, we are trying to measure horizontally, right? There's our radius right there. We're measuring a horizontal distance, so what letter do we want to isolate in the equation for that line? We want to isolate x or y?
X.
We're measuring horizontally, we always isolate x. So this will be x is equal to y over 4. That's the radius. X over 4, excuse me, y over 4. Y over 4. Y over 4 is the radius. So the pi, we factor it out to the front. What goes in here? Y divided by 4 quantity squared. That's the radius squared. So the radius squared is all that. So we had to write the radius as a function of y. That means we find the equation of this tilted line, solve for x, that's representing the radius. And now we should be able to put it all together. So do you see that this is going to be a 16 in the bottom that can factor out to the front? So that 4 squared is 16, so we're going to end up having a 9,800 times pi divide 16 out in front. And on the inside, we're going to go 0 to 6, and we're going to take this y squared and distribute it so that we have 6 times y squared minus y cubed dy. There is an easy integral, all the way down to a polynomial. So we'll deal with these constants in a minute out here. We'll just leave it for now. Something might cancel. So we're going to end up with 2y cubed minus y to the 4th divided by 4 from 0 to 6. Plugging in the 6. We're going to get 6 times 6, which is 36, multiplied by 6 is 216. So we're going to have, and maybe I'm going to do it this way. I'm going to do, well, it doesn't matter. I'm going to just type it into my calculator, I think. So 2 times 216 minus, this is going to be 36 squared, whatever that is. Who cares right this second? Divided by 4. So we just have to simplify all that. And we'll leave the pi in there. We won't take away the pi. So we're going to have all this stuff. Minus 36. 36 is squared. Divided by 4. So that's all 108. So this is going to be 9,800 times pi divided by 16 times 108. So divide by 16 times 9,800. And I'm getting, hopefully somebody can confirm this. Come on. So 66,150. Oh, good. Oh, good. All right. So, yeah, cone, a little bit harder than the cylinder, but not as hard as the trough. So we've done the three-dimensional cases in all three examples. We've done the cylinder, we've done the cone, and we've done the trough. So the three-dimensional case, in a lot of ways, is easier than the one-dimensional case. Let's go back to the one-dimensional case. So the one-dimensional case, the rope and the chain, there's something that's missing, and here's what's missing. So volume is 3 dimensions, right? And when we go down to 1 dimension, we are taking away 2 dimensions. So instead of ADD volume, if we chipped off 1 dimension, we'd have ADD area. And if we chip off another distance, we'll have ADD length. All right? So this is going to be ADD length. And wasn't the dy part of the volume? Right? It was the vertical distance that took a cross section and puffed it into a slice. So this length is dy. So when we were finding volume, we did cross-sectional area times dy to get volume. Now we're swiping away the area part. So instead of volume, which is area times thickness, now we just have thickness or minuscule height, which is dy. So that is what we are going to use, is ADD length, and that length is dy. Whatever's in these parentheses always includes the differential. And if we're only down to one dimension, the differential has to be there. So it's just dy. Okay, so here we go. So we're imagining this 60-meter rope, and the 60-meter rope is hanging over a cliff. So we've got a 60-meter rope dangling, hanging freely from a ledge. And the density of the rope is given right there. The diameter of the rope is given. How much work is done? All right, well, let's be careful here. So the work is going to be the integral A. Okay, that's acceleration. That doesn't change. Acceleration, density, distance. Density, oh, they gave it to us. Here is the density. 55 grams per meter. Now, what units do we need for mass when we're using the standard metric system? Kilograms. So we have to be a little careful here. Meters is fine, but we have 55 grams. So to turn that to kilograms, we have to use a conversion factor. So we have 55 grams per meter. I'll just write the units here for a second. What is the number of kilograms in a gram? Excuse me, other way around. How many grams are in a kilogram? 1,000. So we're going to do this. So there is our density. So acceleration, density, and then distance. So let's take a piece of rope, a cross-section of rope. Cross-section of rope is just a point. Because we're in 1 dimension, we're not in 3 dimensions. In 3 dimensions, a cross-section was 2-dimensional. But for a rope, doink, right there, there is the cross-section of rope at a random y. That's our cross-section of rope. It's just a point of rope. And so acceleration, density, distance. how far does that point of rope have to travel to get to the top where it's being pulled up? 60 minus y. That is going to be the distance traveled. Right? This distance is y here. This distance right there has to be 60 minus y. So there's our ADD. And now length, super simple. It's just dy. It's a little length of rope. We take the point of rope and add a little length. So we're just pulling it in the vertical direction, making it a dy. That's a very small piece of rope. And then if we're going to do the entire rope, limits of integration should be 0 to 60. 0 to 60. So there is our setup. So if we factor all this junk out to the front, we've got the 9.8 out in front. 1,000, we just moved the decimal point 3 places to the left. So we're going to have 0.055. And then we have the integral from 0 to 60 of 60 minus y. dy. So we'll multiply those two decimals together. 9.8 times 0.055. I'm getting 0.539. That's going to be polite and change this to a fraction easily. So 539. I guess that's one way to change to a fraction. And then we integrate here. We'll have 60 times y minus y to the 2 over 2. And that's 0 to 60. So this will be 539 over 1,000 multiplied by, plug in 60 there and we get 3,600. Multiply or subtract off 1,800. So we're going to get 1,800. So whatever that simplifies to, we're going to have a pair of zeros that just vanish right away. And I guess the 2 vanishes right away. So divide 2 with that, we get 9. And that should be about as far as we can go. So 539 times 9 divided by 5. So 539 times 2, no, 539 times 9 divided by, oh, I guess that's all we have to do. So 4851 divided by 5 joules. So it's funny because the one-dimensional case mathematically is a lot easier because you just have the dy instead of that whole volume business. But it's a little harder, it's harder to conceptualize that this whole thing just turns into the dy. So you just want to think about with the volume, you took area times dy, but when we go from 3-dimensional density to 1-dimensional density, we're taking away 2 dimensions, so we're just left with the dy.
So why did we use the diameter?
It's extraneous. We don't need it because we're dealing. So the question is always, are we in a 1D situation or a 3D situation? How do we know we're in a 1-dimensional density problem? Because the density is given to us as 1-dimensional. They didn't say 55 grams per cubic meter. So if they gave us 55 grams per cubic meter, then we would know that we need to have cross-sectional area multiplied by thickness. But because this right here is 1-dimensional right there, that is how we know. So that is 1D density. So this right here is extraneous. Don't need it. Yeah, good question.
Why do we have to just go over 1-dimensional and 3-dimensional and not 2-dimensional density? Is it not important?
It is important. You'll do it in Calc 3.
Oh, it's okay.
Yeah, you will do it. They call a 2-dimensional thing lamina, and you do those things in Calc 3.
Okay.
Yeah. we're doing things that are, kind of more, I don't know, a little less. The 2D case is a little more complicated than the 1 and the 3. So yeah, you'll definitely do it. So let's do a chain one. So very similar. So we've got a 30-meter long chain hanging vertically from a cylinder attached to a winch. Assume there's no friction. Yeah, we hate friction. And in the system, and the chain has a density of 5 kilograms per meter. Little bell, one-dimensional density, kilogram per meter. We're happy that they gave us kilograms. We don't have to do any shifting by 3 decimal places. So let's draw a little sketch. We've got our winch up there, and our rope is going to be hanging 30 meters or chain, whatever you think of it as. So we've got our 30 meters. Ground is down here. If we pick a little piece of chain, we're going to think of that piece of chain at a height of y. All right, and so first off, let's set up our work equation. Work is going to be the integral of ADD. And because it's one-dimensional, it's not ADD volume, it's ADD length. And right away, we know that the A is 9.8. So that's kind of automatic. That's autopilot up to there. And then the density is given to us with the proper units. We've got meters, we've got kilograms. So we know that that's just going to be a 5 for density. So acceleration, density, distance traveled. How far is that speck of rope going to travel? So that distance right there will be 30 minus y. Right, the whole length is 30. The height of that speck of rope is at y. So the leftover is 30 minus y. So it's the whole thing minus where it's at. 30 minus y. And then the easy part that's hard is the length is dy. Just dy. We have one-dimensional density, and we're going to lift up the whole rope, I think. How much work is required to wind the entire chain, or the chain? There it is. All right. So whatever that is, that's not too hard to integrate. 30y minus y squared over 2, plug in the limits. So let's not actually compute that. Let's take a look at the second one. So that's part A. Part B. How much work is required to wind the chain onto the cylinder if we up the ante? We up the ante and we attach a block to the bottom of it. So let's attach a block, a 50 kilogram block. So that 50 kilogram block is really easy to analyze all by itself. If you were to lift a 50 kilogram block, that's just mass, that's just mgh. It's mass times gravity times distance traveled. Because that's now a constant. This whole thing is being lifted up. You don't you think of it as a point mass. You don't have to separate it into little slices. So if you just take this 50 kg block and lift it, it's going to be the mass, mgh, mass times gravity times height or distance traveled. So what we're going to do then in part B is we're going to take this whole thing is for winding up just the chain, and we're just going to add as a separate problem how much extra work is done if you have to lift a block 30 meters. So it's going to be whatever this is. Let's call this, so there's our answer to part 1, which is not too hard to find. So we're going to take whatever is in part 1, we're going to take that, and we are going to add mgh. So the mass is 50 kilograms, mass, gravity is 9.8, and then the distance traveled is 30. So we're just going to add that onto it. So this is the work done to lift a block. work to lift a block. And that's it. So we can treat it as two separate problems. How much work is it to crank up that chain? And then separately, how much work is it to lift a point mass? And so the total work for that whole thing will be that. So this is MGH. Mass times gravity times distance traveled or height. mg is force. mg is force, so force times distance gives us work. When you're going vertically, force is m times g, mass times gravity. Next problem is really interesting. I find this very fascinating because being a math person, when I set up these things, I like to draw the picture so that it matches what the physical reality of it is. So here's the scenario. 40-meter chain, simple density, 1 kilogram per meter. It's hanging from a winch. How much work is required to wind it up halfway? So here's how I would do it as a math person. So there are two ways to do this. One that matches the reality of the physical problem, which is the way I would set it up as a math person, not being a physics person. And the other one is to take the initial state and then compare it to the final state in a much more conceptual physics type of approach. So here's the reality method. We just talked about it. So here we have it. So the reality method, we're only going to wind it up halfway. So here's the full 40-meter chain. The whatever color that is, beige, those beige dots physically represent the links of the cable that are going to be wound up onto the winch, right? The black part there, that's like a hanging block. So if we were to wind up the beige blocks, this is what it would look like, right? And this bottom half is just being lifted, so you can imagine it like the beige plus a block, and the block gets, the block's just being lifted. Right? We can take all that chain, the lower half of the chain, and imagine it as just like a block. And so that's how I would do it. I would say, oh, so the chains that are moving, the links that are moving are the ones from 20 to 40. Those are all being wound up. And then down here, we can figure out the mass of this block and then just do MGH. All right? That works. You will get an answer. Then I had a physics person many years ago say, well, why don't you just do it this way? And I was like, what? And they just integrated from 0 to 20 ADD length, got the same answer. I was like, I don't know. Why does that work? And with this approach, you can take the initial state, and the terminal state is that there are 20 meters of links that are hanging. And you can think of these 20 links here as being transported to the top. And we can say, well, that we know that there's going to be 20 meters hanging in the end. Let's just pretend it's these 20 meters that are the top half of the chain. And let's imagine just focusing on the black dots, the bottom half of the chain. How much work will it take to take those 0 to 20 and transport them to the top? And so that's what this does. This finds the work done to transport these links from 0 to 20 to the top. So you integrate 0 to 20, ADD times length, and you will get the same exact answer. So totally up to you which approach you want to use if you have a chain with a chain that's only being partially cranked up. But it's fascinating. It's a good exercise for you to find the work done in this case, find the work done in that case, and show to yourself that it is actually the same. Very, very interesting, I think. Yeah, so as a math person, the reality method feels like more like, okay, I get the reality method. I get that the lower half is just hanging like a block. So let's just figure out the work done in lifting that block. So, yeah. So let me talk we won't have time for an example, but let's just talk about the last chunk of this section. Let's see where we at, force. So, the acronym of the day has been ADD volume. And if we look at all the units, ADD volume turns to units of work. Okay? So that's why we use it for work. Now, the next examples at the end of this section are finding the force on a wall. So we are going to imagine a dam, and we're going to imagine water pressing against it. And we want to know, oh, well, how much force is pressing on that dam? That tells us how thick we need to build the dam, etc. And force is one dimension down from work. Right? Work is force times distance. Work is force times distance. And if we take off the distance, we're left with force. So if we take off one dimension, we're finding force instead of work. So instead of ADD volume, if we take off one dimension, ADD area, that will find the force on the dam wall.
Will we also do an example of a trapezoid?
Yes, we'll do that in this. Yeah. Yeah, we'll do that with this. This is going to be very similar. Let me ask you to think about one thing before Thursday. Think about this, and we'll talk about it on Thursday. Let's suppose we have a trapezoidal dam. So right there, got this trapezoidal dam, and then back here is the water. So let's suppose that this dimension right here is, say, 2 miles of water pressing against this dam. And what I want you to think about is, what if we extend this another mile? So let's go 1 more mile. We're going to add, because maybe we've got this dam built and we're like, we need more water in our reservoir, so let's just extend it. The question then is, what does this extension by 1 extra mile do to the force on this dam here? So think about that for Thursday. We've got this dam set up. We've got this 2-mile reservoir behind it. If we want to add another mile of water, how much extra force will there be on that dam? So just think about that for Thursday. Just think about what your intuition is going to tell you. It's not, don't go find, well, you can go find the answer if you want, but think about what your intuition is going to tell you. And I will see you all on Thursday.
Jim, are you office hours?